All right. Now we're going to be talking about the lists. Um, as you know from operating systems, we have a lot of queues that we deal with. Um, Ready queue, waiting queue. Even you could have theoretically a running queue if you have more than one CPU that is running, right? So we do need to define a list, okay? Again, here you have if not diff list, define list, and in the end here end if. I have talked about this before and I explained why we need this, basically to prevent the compiler from seeing whatever that is defined here replicates. So we prevent those from being defined more than once. Otherwise, you're going to be getting a compiler error. In this one, we define something called list node and another one called linked list. I'm quite sure you have seen that in data structure and in advanced C. Let me explain that in a clear way. Here is the link, sorry, in the node. You have here item, so data item, whatever that is, here it is. Why do I define it as pointed to void? I want to create a linked list, a single linked list that can have any type. So it can have, it could be a list of events or a list of CPUs or a list of integers or list of characters or list of whatever you want to name it. Not only that, but every node in this way can have its own type. So one node is pointing to event, another node is pointing to process, a third node is pointing to an integer. That's not what we are doing here in the project, but yes, if you do it as pointed to void, it does give you that flexibility. So here is the node, as you can see. It has here an item. Here you have two pointers. One is pointing down, we call it next. One is pointing up, we call it previous. We called that in data structure and advanced C to be double linked list. Why do I define it as double linked list? For ease of search. So if you have something like here, like that, the linked list would look like this. Okay, so if you have a pointer here, you want to go out, all you need to say is, let's say this is called current. So all you need to say is current equal current points to previous. So you bring it here. If you want to go down, then current equal current points to next. So you come here, okay? So it's much easier to navigate when the linked list is double linked list. The exact same concept here, type def struct linked list underscore node, and then we gave it here an alias. Why do we give it an alias? So you don't have to write the word struct every time you want to define list node. After you defined a single node, now we want to define the whole list. Yes, you can do a single pointer, which is possible, but it's much easier and faster. When I say easier here, we're talking about complexity, okay? As engineers, of course, you measure everything with complexity when it comes to code. So if you don't use two pointers to define the list, then the complexity of the algorithm is order n, if you remember the complexity, order of n. Whereas, because I defined it to be two pointers, is going to be order of k, constant, which reduces the complexity dramatically. Okay, how do we do that? We define in the linked list two pointers. One is, I'll call it front and rear. You can call it first and last, whatever you want. Here is the front. here is the rear, and whatever, from the front all the way to the rear is your linked list. That speeds up the process of the linked list dramatically, as you will see later. So here we defined the two types that we want for a linked list, and then few function signatures. Here, create list node, so you want to create one of those. Create list, you want to create one of those as a list. Okay, add front, so you add to the front of the list. Add rear, you add to the rear of the list. Add sorted, so add sorted means you put it where it belongs. So if you have something like 3, 5, 7, 10, if you want to put 8, it would be here. If you want to put 6, it would be here. If you want to put 4, it would be here. If you want to put 1, it would be here. If you want to put 10, it would be here. Okay, so where it exactly belongs, so that would be add sorted. Okay, what does it take? We'll talk about it when we go for the code. Here, delete front, so you delete from the front node, delete rear. Okay, we have get minimum. What is get minimum? You will see it in the code. It gets you the minimum node. What does it mean? If we're talking about first come, first served, then the minimum here is the minimum arrival time, right? Because that would be the first come, first serve. If you're applying shorted job first, so the minimum would be the burst. If you're applying shortest remaining time first, so the minimum would be the remaining time, and so on. The priority, then the minimum would be the minimum priority. Okay. You have also a function called get item, and then delete item. Okay, print list, destroy list, and you have here another destroy list that has different inputs. All right, and you have here a function, I called it empty, that tests whether the list is empty or not, and you have here a function length that returns the length of the linked list. Let's look at the code. Of course, here the list, you're not really required to know it by heart, because this is more programming than anything else, but I will explain it in case you want to understand what it is. Here, again, we're including the studio, the stdlib, and, of course, list.h. This is the C code, right? So how would you create the list node? Again, here you define the list node, pointer node, that's the one that is going to be created, equals malloc. You have to typecast it to be list node and size of list node. Okay, I explained that in details before, so that's why I'm going through it very quick. After you create the node, you say that now that this is a new node, here it is, this is the node. It's just created, it doesn't have a previous, and it doesn't have a next, and it doesn't have an item. There's nothing here yet. So the previous is going to be a null, the next is going to be a null, and the item is also null because it's defined to be pointer to void. So null, null, and then return the node. So basically what you did is you just created the structure of the node and put here to be null, here to be null, and here null. Okay, if you want to destroy the node, okay, I'm sending it to be called by reference. That's why I'm putting it as 2 stars, because the node itself is a star, and I'm gonna be changing inside the node, and I'm gonna be changing the node itself. So that's why you have to put 2 stars. Okay, if you have 2 stars, that's how you access the next. Star node points to next equals null. I'm destroying it. Star node points to previous, it's null. And then I use free. What is free? Free is the opposite of malloc. If you don't remember that, go back to Advanced C. like revise, I mean advanced C, and here is free the node, and then the node is null. That's how you destroy it. You're going to use it. You don't even need to use it. Here we want to create the list. Same exact way. Here you're going to be using a malloc, and here is your list. The front is null, the rear is null, and then you're going to be returning the list. Why? Because you just have a list. There's no nodes inside it yet. So the front is null and the rear is null. Now, when you want to add to the front, let's understand this together once and for all. Initially, the list is null, so you have the front is null and the rear is null. Now you want to create a node, so first you have to create the node itself. How would you do that? Here it is, new node equals create list node. What is create list node? It's the method that we just talked about it in the beginning here, create list node. It creates the node, puts the next to be null, the previous to be null, and the item is null. Okay, so you created this is the node, here it is. After you created the node, you say that you want to put it, look, add front. What does it mean? If you have a list here, assume that this is your list. You want to put that on top. This is gonna be the front. This is gonna be the rear. Let me continue drawing it so you understand it. Here. Okay. So you want to add this on top. How would you do it? If this comes on top of the list, then the next will point to this. So the next will point to the front. And the previous of the front is going to point at the node. And the previous of the node is going to be null. And then the front is no longer here. The front is going to be here. So how are we going to be doing this? Look at that, the steps. New node points to previous is null, here, null. The next is list points to front, as I told you. This is going to point at the previous front. And then the item is the item that you want to insert it in. And then if the list points to front not equal null, then the previous is the new node as well. See, if this is the new node, then this previous will point here. And then that becomes the front. So how would you say that? Here, you know, list points to front equals the new node. And then you return the list. What is this? See, now what if the list is brand new? It doesn't have any nodes yet. How are you going to be doing it? You created the new node. Here it is. So this is the new node, right? Now the previous is null. And the next is the front, which is null, because the list in this case is new. So this is the front, but because this is the one and the only one node in the list, it's also the rear. If you have one person in class, that person is the first person and the last person. So here it is. If the list not null, okay, so the previous of the front is new node. If it's null, then the rear is the new node as well. So here, the rear. So in this case, the front and the rear will point at the same node in case it's a new item that is being added to the list while the list is empty. How about add rear? Here it is. Again, you're going to be creating the new node. The next of the new node is null. Why? Look at that. If you have the list here, assume this is the list. sorry, and now you have a new node like this. This node is going to be added to the rear, the end of the list, so it will not have any next. So the next is always going to be null. Here it is. See? New node points to next equal null. How about the previous? New node points to previous is the list points to rear, the last node. The rear is the last node, correct? So how about the previous? The previous is going to point at the rear of the list. How about the next of the rear is going to be the new node, and then move the rear one step down. Here it is. Look, new node points to previous equals list points to rear, and then new node points to item is item. That's the one that you want to insert inside the node. And then if the list points to rear is not null, put the next of the rear to be the new node, right? Else put the front to be new node, because it's going to be the one and only one node, and then the rear is the new node. Okay. Now at sorted, at sorted here, you want to put it either in front or in the back or in the middle. Okay, I don't want to make it harder for you, so this is the code I compare based on the values. If you really want to understand the details of the sorted, then please don't hesitate to come in the office hours. Okay. Same applies to delete item, delete front. Let me explain delete front because it's not that hard. Here it is. If you want to delete front, of course, you have to have a front first for it to be deleted. Again, whatever that I skipped, if you want to understand, please come and visit in the office hours. If this is the front here, you want to delete the front first, make sure that the front does exist and the list does exist. How would you say that? If the list not equal null, and then if the list of front not equal null, what will you do? Let's point with the pointer here, move the front one step down. So the front is now here. Let's remove this link and remove this link. How would you remove those links? You're going to put them with nulls and then delete this one. How would you do that? Look at this. To be deleted equal the front, because you want to delete the front. Here it is. I pointed at the front with to be deleted. And then move the front one step down. Front equal front points to next. Here it is. Now the front is pointing at here. Then to be deleted points to next is null. So remember, it was pointing here. Now it's null. And then if the list of front not equal null, the previous of front is null. So this link is also going to be cancelled. And then now you want to free the whatever that is inside here, if it exists, and then delete the node. How would you free it? Using the keyword free. Of course, you return. Same with the delete rear, print list, destroy list. You delete all the nodes in there. Empty here, all you do is you compare whether the front is null or not. If it's front, then yes, it is empty, so you return 1. 1 means yes. Otherwise, you return 0, which means no. Okay. The remaining 3 functions, one of them is get minimum. This is one of the most important functions in the list that actually does dictate how the list will function. So you send the list, you send function called compare. Yes, in C you can return, like send a function, a whole function. Okay, so you say if the list is null, return null because there is no comparison here. right? If the length is 0, you're gonna also return null because the list is there, but there's nothing. If the list has a single item, then this single item is the minimum because it's the only one. Otherwise, here you're gonna loop, and each and every time you're gonna call the function compare. What did the function compare look? It's the function that you have send, and you send the minimum. I went through it very quick because I do understand that this is a little bit complex. I did this way to minimize the number of code that I need to write, but I don't want to bother you much with it. If you really want to understand how this works, please do not hesitate to visit me in the during the office hours, okay? That's enough for the linked list, since the linked list is, while it's a core file in the code, it's basically C, so it's not really related to operating system, so it's enough for this file. And let's move to the operating system files.